All right, recording is rolling. It is Friday, December 9th. We're going to start the midterm review today. Oh, okay, good. Thanks. Yeah, so this will take us a few days. And tell you what the midterm's going to be. I'm giving you guys 100 multiple choice questions. You guys want to do open notes? Open notes for midterm? All right. So any notes you guys have taken, any notes you guys take today or next few days, can use those to help you out. Oh, so you guys did pretty good on the quiz yesterday. I do have this graded, so you're right on focus. I have not handed them back yet. I'll let you guys do quiz corrections, but I still got a few students that need to take that. So it'll be a tight fit, but we'll able to get all that in. You guys see this page in front of you right here? So it's midterm review. There's 100 conceptual questions. All right, so this is going to be a part of the review. Now, I'm not going to exactly go over these exact questions today, but next week we will. We'll hit all these. So this is for you guys. So you guys have one of these. You guys pick up one of these. Right, and keep that. I have posted this to Google Classroom along with a few other things. So let me. Oh, right before I switch my screen, let's take a look at the midterm schedule. So next Friday is your first exam, and that's your 7th period. Okay, so 7th period kicks off next Friday. Okay, and then the week after that's going to be a 3-day week, and you'll have 2 classes each day. So it's going to go first, second, third, and fourth, 5th, and 6th. Right. So you guys are third. No, this third period, right?
This is third.
Third. All right. So yeah, your physics exam then is going to be on Tuesday the 20th, right? Right. This midterm schedule I have uploaded to Google Classroom also. Okay. So you guys got that? All right. Flip my screen over here. All right. Here is Google Classroom. Show you guys what I got here. So midterm study guide, that's that half page. Okay, I'm kind of wary to click on some of these just because I clicked on one of these earlier and it just like disappears. So I go, I don't know what that was about. But that half page in front of you with 100 questions on it, that's under midterm study guide. That's right there. Right. Midterm schedule, I just showed you guys that. So that's right there. Oh, Spirit Week flyer. So I've opened that in a new tab right here. Monday is holiday hats and socks, and day after that has fun stuff going on. So if you want access to that, that is right here. And then today I'm going to take you guys through a PowerPoint that spent a lot of time put together over Thanksgiving break. So it has animation and all in it, and that's right here. So that's for you guys. Okay. All right, so a bunch of good files right there. All right, let's get going on this PowerPoint. All right, so starting at the beginning. There is a dot for every day in your life. Life goes fast. Make the most of it. Orders of magnitude. So these first few slides have to do with measurement one way or another. There are 1,000 bubbles there. You guys know the prefix for 1,000 is kilo. Kilo is the factor of 1,000. 1,000th is milli. So for example, 1 kilogram is 1,000 grams. 1 millimeter is 1,000th of a meter. There's a million dots there. Million is mega, or 1 millionth is micro. For example, megahertz, micrometer. Right? Scientific method. Different textbooks have a little bit different variations on this, but usually start off with some kind of question, problem, something like that. Usually do some kind of background research, right? And then you want to formulate a hypothesis so you can conduct an experiment. There you go. Hypothesis is usually called some kind of educated guess. If you can quantify it or guess some kind of formula, that's usually better. Yeah. All right. Then experiment, gather some data. Then you want to crunch that data with the analysis. The version of that we've done in this class is a lot of times we'll create graphs, find graphical relationships between variables. Sometimes it's linear, sometimes it's parabolic. And then you can come up with some kind of conclusion, which might be an equation like, oh, x equals 1/2 at squared. Or it might be like the last lab we did was we said the rotational inertia, that crazy pipe system is like 0.06 kilogram meter squared or something like that. Okay. So scientific method, again, different textbooks might have different variations on that. Oh, is my screen frozen? Oh no, we're good, we're good. Okay. 7 base SI units. So these are them. And really this semester, we've only dealt with 3, the top 3, kilograms, meters, and seconds for mass, displacement, and time, right? And we've combined these all different ways to create composite units. For example, force measured in newtons is kilogram meter per second squared. Energy measured in joules is kilogram meter squared per second squared. Okay. Next semester we'll hit some of these other ones, but there you go. Right, so 7 base SI units. And those top 3, which again, all we've really dealt with as building blocks for our units this semester, Here are the original definitions back in the 1790s. So fun history right there. There's some universal constants. Nobody knows why these numbers are what they are. And there's really only a couple here that are really relevant to you guys. Gravitational constant, 6.67 times 10 to the minus 11 newton meters squared per kilogram squared. We've used that one a few times. The speed of light is going to come up next semester. We'll use that a little bit. Elementary charge that you guys will see, maybe Planck's constant, tail end of this class. This one you guys want to cover. So there you go, some universal constants. Scientific notation. So mass of the Earth is huge. Guys, could you call this 5.97 times 10 to the crazy power kilograms? Boom, just like that. Mass of a proton, tiny, tiny, tiny. Can I call this 1.67 times 10 to the negative something? Yeah, something like that, right? Yeah, so crazy, right? Oh, a negative exponent. That doesn't make the number negative. It makes the number tiny, right? It's like you're dividing by 20, dividing by 10, and you're doing that 27 times. SI prefixes. So here's one list, but here's maybe a slightly more relevant list to you guys. Right. So if you go from this is powers that are multiples of 3, so 10 to the 12 to 10 to the negative 12. Right, really big to really small. Boom. So prefixes that are good to know. Right. Accuracy and precision. If something's more accurate, that means like it's more correct. If something's more precise in a numerical sense, that means like you have more digits to work with. Give you guys an example over here. C could be the speed of light. I might say the speed of light is 3 times 10 to the 8 meters per second. That's true, but if you want to get more precise, you can go up this page and get more and more precision. Right? Like more exactly true. Dimensional analysis. This is a tool that hopefully you learned in chemistry, and then I reviewed with you guys at the beginning of this class. And we've used this over and over again in this class. It's really good for converting or for making sense out of maybe if you don't know what an equation could be, but you know some units, you can kind of do some unit analysis. Right? If you had $1 billion and spend $1 every second, how long would the money last? If you run the numbers, it ends up being about 31 years, by the way. I think a recent example of dimensional analysis is we converted radian or revolutions to radians. Right? Use this method. Right? So use this all over the place. It's a really handy tool. I've just used this in my everyday life too for different things, like calculating the fuel efficiency in my car. Different things. Scaling. What if you have a little box down here? So you guys see this little box down the left? Okay. And you scale each side up by a factor of 3. So, well, the box is 3-dimensional, right? So anything that's linear, for example, if you walk around it like the perimeter, we'll also scale it by a factor of 3. Anything to do with area, for example, how much paint do you need to paint the surface of the box? That's a scale factor of 3 squared because 2 dimensions, factor of 9, so 9 times the paint, right? And what if you filled it with water? Right. Well, that's 3 dimensions. So scale it by factor of 3, 3 dimensions, 3 to the 3. That's 27 times the water. So the big crate compared to the little box. Right. Scaling. You guys remember scaling? Right. This is a bunch of different useful applications in physics. I think this will pop up in the future too. Right. So as you scale up something bigger, different properties will change at different rates. Algebra. I mean, algebra is something you do so much in this class. I mean, you definitely got to know those by now, right? Classic algebra problem has 2 answers. Right? This is how you solve it. Right? There's some middle stuff thrown in right there. Right? I did tell you this whole presentation is on Google Classroom, right? With all the animation stuff too. Right? So you guys have this. Use a great study tool right here. Right? Quadratic formula. If you get a formula in this form, this refers to parabolas, and you're solving for like some specific values for parabolas. It usually has 2 answers, although it might have 1 or 0 answers, but it usually has 2 answers. Right? And a classic example in physics is if say you throw something upwards and it comes back down, well, height as a function of time is going to follow a parabolic relationship. If you want to know what times was it at some specific height, you could use this and solve for that. Right? What's the formula for that line? Y equals mx plus b. Boom, just like that. Right? Y equals mx plus b. Right? Now that's a linear relationship. There are really only a handful of relationships that have shown up in this class over and over. Right? If there's no relationship between variables, you might get a horizontal or a vertical line. Just one variable could change and the other variable doesn't care at all. Right? For example, when you guys were rolling those Hot Wheels cars down the incline, we're changing out the mass. Changing out the mass had nothing to do with the kinematic motion. So like mass function of time, it's just like that. Linear or direct, you might get something like that, like y equals mx, y equals mx plus b. Okay. Inverse relationship. What if one variable gets big and the other gets small? Okay. For example, Newton's second law of motion. What if you applied a constant force to different masses? Well, the more the mass, the less the acceleration, right? Vice versa. Right? Parabola show up all over the place in this class. A root is just like the inverse of a parabola if you just swap the axes. So you kind of height versus time here. You can have time versus height. Same idea. Sinusoidal. Has this popped up in this class yet? I don't think it has.
Once.
Maybe once. Right? I think it'll pop up pretty soon in January because we're about to go into pendulums, like harmonic motion. So if a pendulum swings back and forth, it's going to have like harmonic motion, oscillatory motion. So it might do something kind of like that. Okay. The Pythagorean theorem. So if you have a right triangle, you guys know that. Hey, also, what is the area of that blue triangle? Yeah, 1/2 base times height. Boom, just like that. Okay. You can also use this on not right triangles. You could have just like a scaling triangle or something. You can still do 1/2 base times height. Just this wouldn't necessarily be the sides. It's really nice on a right triangle because the sides could just be the base and the height. Okay. Vector components. So on the left are the definitions of sine, cosine, and tangent. So this is like what's programmed into your calculator, okay? As it corresponds to that picture. But how we use this, how we actually apply this in this class, like 95% of the time, is like you might know what C and theta are, and you're trying to figure out what are A and B, those components. You guys should probably know this like the back of your hand by now, right? That B is C times sine theta and A is C times cosine theta. And we've done that like probably literally hundreds of times in this class, right? Right. So you guys know that. And then this last box, can you guys extract theta if you know the sides? Right? There's one way to do it, right? You needed some kind of inverse trig function. Okay? For example, inverse tan, ratio of sides. Car drives at constant velocity. Okay? Let's set up 3 graphs: x versus t, v versus t, a versus t. Would you guys be able to draw those graphs? If I asked you, are you guys either writing in your notes or imagining what those graphs look like? Constant velocity. So your cruise control driving up I-95. Did you guys just come up with boom, boom, and boom, just like that? Right? Because x versus t, you're picking up displacement at a constant rate. Okay? In fact, the slope of that is how fast you're going, like the speedometer reading. Okay? The next graph, the speedometer reading would be constant. That's what constant velocity is. Okay? So the needle's just pointing as a constant number. Okay? And there would be no acceleration, okay? Because constant velocity. Okay, boom, boom, just like that. Hey, can you feel how fast a car is moving? No, you can't feel a change in motion. Right? That's what acceleration is. Right? The acceleration is a rate change in motion. Could you guys write the formula for linear acceleration? How's that formula go? It's the rate it's changing its velocity, right? Is that change of velocity per time interval? You guys remember that, right? But you can rearrange that and it looks like one of those kinematic formulas, right? Vf equals v naught plus at. Okay? And there's another kind of acceleration, which we didn't actually get to until about halfway through the semester. What if you have a constant speed, but you're changing direction? Ooh, that's changing velocity also. And what's the formula for that? You guys were thinking of v squared over r? Because we're doing a lab with the Plato canisters that PV's got mv squared over r for the centripetal force. It's related to that, right? Okay. So you can feel changes in velocity. 3 kinematic formulas. Hopefully you guys have these memorized by now. If for no other reason, just you've applied them so much. I mean, they keep popping up over and over and over again in this class, right? So there are 5 variables here. If you know any 3, you can, if you can identify any 3, you can solve for the other 2, kind of deal, right? We got displacement in meters, velocity in meters per second. Might have initial final velocity if there's an acceleration, and t is how much time has passed in seconds. Right? Here's the same thing, just looks a little cleaner right here. Okay, identify any 3, solve for the other 2. Hey, what if you go to the edge of a cliff and you drop a ball and you're on Earth, so it's accelerating down at 10 meters per second squared, and you let it fall for 1 second, and it falls 5 meters. Now that would be true as long as you dropped it, which means you released it from rest. And you could also calculate how fast it's picked up to, right? So, oh look, I must have released it from rest, and oh, if it fell for 1 second, it's picked up to 10 meters per second. Right? Right. Here's a table for like all these values, right? So drop a ball off a cliff. That's a scenario. I'm going to call down the positive direction. Count off the seconds. 1, 2, 3, 4, 5 seconds have passed. Right? It's always accelerating at the same rate. we're ignoring air drag. Right? We're rounding a little bit. You guys know this is really like 9.8, but I'm rounding a little bit. Right? It's meters per second squared. Right? And how fast is it going? Well, if it's accelerating at a constant rate, that means it's picking up 10 meters per second every passing second. 10, 20, 30, 40, 50 meters per second. In the last column, how far is it falling? Now that has a parabolic relationship with time. So see how it's like spreading out? It only fell 5 meters during the first second, and then it fell, now it's going a lot further. Okay. You guys remember the story? Paul Hewitt goes into an old cave, finds an old mine shaft with his friend. Like, hey, how deep is it? So they drop a rock, you count to 5 for bam, the rock hits the ground after 5 seconds. It's about 125 meters deep. How'd you know that, college? Hey, look right here. 5 seconds, tick, 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 tick. How far is it falling next? 125 meters. Okay. That is that story right there. Okay. And that's x equals 1/2 at squared, right? Could you guys draw the 3 graphs for that story? X versus t, v versus t, a versus t. You guys know what those 3 graphs look like? Right? Either you're jotting them down in your notes or you're imagining what those look like right now. Right? So you guys always said this, right? So yeah, got a parabola for x versus t. Got constant slope for v versus t. That's a linear relationship, direct relationship. Okay, and a constant acceleration. And for free fall, you just call it g, like 10 meters per second squared. Okay. And everything in green and red tells you the relationships between these 3 graphs. Like if you know one of these graphs, you can figure out the other 2. Okay. And what if you don't drop the ball? What if instead you throw the ball? And you could either throw it up or down, just staying in linear motion, right? You go up or down. Right? So I'm going to define down as the positive direction. That's my default, right? Down is positive. We'll call the top of the cliff like 0.0, right? Let's start with throwing the ball upward, right? Throwing the ball straight upward. Okay? So remember, down is positive, so up is negative. So let's start with this middle graph right here. Okay? If you throw it upward, aren't you throwing it into the negative direction? Which means it has a negative initial velocity, and then gravity is going to pull it the other way eventually, right? Bam, just like that, right? Okay. You guys remember what those other 2 graphs look like for throwing a ball upward? Okay. So, okay, well, constant acceleration. Right? Actually, if you only know the acceleration, you don't really know which direction the ball's going. You just know it's in free fall. Right? And how about x versus t? See, I'm throwing it upward. That's the negative direction. It's eventually going to come back downward, the positive direction. It's that bam, just like that. Where it goes to 0 velocity, that will also mark the point of maximum height. Okay. Okay. What if instead you chuck the ball straight downward? Okay. Okay. Hey, how about this? Okay. Suppose I have 2 balls. Right? I throw one straight up, right? Wait for it to peak and then come back down. And right as it's passing me at the cliff top height, I throw the other one down at the exact same speed, right? Won't those 2 travel straight down side by side all the way down, right? Which means that these 3 graphs we're about to get should be some slice of the 3 graphs that are already up here, right? So throw the ball down, it's in positive direction, bam, 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 just like that, right? See how these 3 on the right are just like slices of these 3 on the left. If I start the time like right here, okay, just the same thing. And okay, so the green and the red tell you the relationships. Okay. Let's take this v versus t on the right. Let's blow this one up real big. Boom. Okay. You guys remember the slope of v versus t tells you acceleration. That's the rate that velocity is changing. That's what acceleration is. Okay. And the area under the curve tells you displacement, like how far. And if you divide this into a rectangle plus a triangle, isn't that v naught t plus 1/2 at squared? Boom, boom, just like that. Right. Car brakes to a stop. Can you guys draw the 3 graphs for that? X versus t, v versus t, a versus t. See, car brakes to a stop. It had some velocity, and then it came to a stop. So the final velocity must be 0 meters per second. Were you guys thinking, boom, just like that? And if you assume uniform motion, which pretty well do in this class, acceleration should be negative, but maybe like a constant negative value. Okay. All right, now displacement versus time, this is maybe the trickiest one to think about. The car is always going forward, so it's always gaining displacement, but it's doing so at a slower rate. So boom, it's like a parabola that bends down. You guys remember this? All right. Cannon, blast a cannonball. Can you guys break that blast velocity into components? Say how fast it's going strictly to the right, how fast it's going strictly up. Right? something we've done a ton of times in this class. Boom, boom. You guys can do that? Right. So sine and cosine components, right? So playing off that angle, sine, cosine components. How about this? Let's go to top of the cliff, blast a cannonball straight horizontal. Okay. Well, how far is it moved horizontally? Well, that's x times v, or x equals v times t. Okay, x equals v times t, right, where v is the blast speed, but it's also the horizontal component of velocity, which doesn't change. We're ignoring air drag. Gravity only pulls vertically. Okay. Speaking of vertically, how far is it pulling vertically? Oh, well, that's just 1/2 gt squared. Right. As long as you either drop the cannonball or blast it horizontal, that'll be true. Right. Right. Let's do a challenge question with this. I'm going to take this. That's the same picture right there. Great. It changed two little things. I changed y to h for height change, and I changed x to d for like horizontal displacement. So we're starting with off those. Okay. Could you guys calculate the blast speed based on the drop height and the horizontal displacement? That was one of your labs back in the day. You guys remember doing this with the lab, with the launcher, went out to the balcony? You guys remember that? Okay. So let's walk through this. I think that the vertical height drop is going to constrain how much time it's in the air for. So let's start with that. Take this red bit right here, solve for t. Boom, boom. Isn't that the time of fall based on the drop height and the gravity of the planet? Okay. Right, now hold on to that. So we're going to come back to that. Let's switch over to the green part. So how far has it gone? Which has something to do with what we're solving for, the blast speed. We're solving for the blast speed, which is the horizontal speed. Okay. So let's get that in terms of those, right? Yeah, like that. Now you guys see a connection. This t is this t. So I can substitute that right there, just like that. Okay, clean that up a little bit. Now you have an expression for the blast speed in terms of how far has it gone and what's the drop height and also the gravity field of the planet. Boom, 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 just like that. You guys can do that, right? Range formula. That was kind of fun. I may drive that with you guys one day. I don't know. It's there. It's fun. Okay. Newton's laws of motion. What's Newton's first law of motion? An object at restful state rest, an object in motion wants to maintain its velocity. Boom. Right? And if anything is not maintaining its velocity, if anything's ever speeding up, slowing down, or changing direction, that means there must be a what acting on it? A net external force, right? Some kind of external force, right? Newton's second law of motion, what does that say? What causes accelerations? A what acting on a what? Boom, yeah, right. Before I say that, maybe some kind of external net force acting on some mass, something like that, right? Cause it to accelerate. Right? I see this, right? Anybody like that? How about Newton's third law of motion? It says what? For every force, there's an equal and opposite reactive force. Right? Now, this is if you have two objects interacting. Right? For example, a cannon and a cannonball, right? Or the Earth and the Moon. Right? The forces between those things are always equal in magnitude. Right? Now, the effects can be different. Right? But why would the effects be different? Why is that when you blast the cannonball, huge change of motion, but the cannon just has a small rebound velocity? Why is that? Because the cannon itself has so much what? So much mass, right? So much inertia. You go back to Newton's second law of motion and say, right, same force acting on different objects, different masses, produces different effects, different accelerations, right? See that? Right. Similar idea for the Earth, right? The Earth wobbles a little bit because of the Moon, right? But the Moon definitely orbits the Earth because it's so much smaller. Right? Same forces though, right? Why are forces always equal and opposite? Here's a really good visual. Suppose you had like a 3-to-1 ratio, right? So the forces are still the same. Said 3-to-1 ratio in terms of the masses. The forces are still the same. Right? Hooke's law. You guys remember springs? Right? Put a force on a spring, it'll stretch. How much does it stretch? Well, it depends how stiff the spring is. You guys remember F equals kx? You can make a graph looks like that, right? Some textbooks throw a negative sign in there, say F equals negative kx. Really depends what force you're talking about. Are you talking about the force on the spring or the force from the spring? You guys remember F equals kx. You can create a graph looks like this, F versus x. The slope is equal to k, the spring constant. You guys remember you had some springs that were not very stiff, like the green and blue springs. You put a little force, it stretches a lot. But some were really stiff, like those red and white spring scales. Right? You put a huge force and only stretches a little bit. The area under this curve represents spring potential energy, which I haven't quite got to in this presentation, but that's what that would be, right? Free body diagrams. Put a dot in the center mass, label all the forces acting on the object. Okay. So a rocket, constant velocity, deep space. Are there any forces acting on that rocket? No. Okay. So what's keeping it going? Inertia. Right? So remember, something's in motion. It just wants to keep doing what it's doing. So deep space, all you need is inertia. Keep going. Okay. How about air hockey puck, constant velocity? Is there a weight pulling it down? Is there a force from the air jets holding it up? Okay. Those are balancing out. Okay. But hey, that air hockey puck's moving to the right. Is there a force going to the right? No. I mean, maybe there's a force to get it going, but once it's in motion, it's just going because, again, of inertia, right? Just like the Voyager spacecraft, right? Just like that rocket, right? It's just going. Apple and free fall. Now, so one at a time here. The left picture, suppose this is in pure free fall. There's no air drag. What's the only force acting on it? It's weight, which I call mg, right? Mass times gravity field. It's weight, gravity force from the air. Right? Now let's consider air drag. Up to this point in the presentation, I haven't yet, but now let's consider air drag. Let's say that air drag is starting to build up, like this middle picture, but it's still accelerating. Could there be an air drag that's a little bit less than the weight? So there's still a net force, right? But the faster it falls, the more the air drag picks up. Let's say it picks up to the point that it's reached terminal velocity. Terminal velocity. Could that be like that? Where they're exactly balancing each other out? Hey, is that apple on the right in equilibrium? Equilibrium? I think it is, right? I think it's in equilibrium, right? That means it's going at constant velocity all the way down. Constant velocity. That's what terminal velocity, right? I bet I could reach that terminal velocity faster with a parachute. Right? There's the equation for drag force. I think I took like 10 minutes one day to talk about this. Okay? By the way, here's a different coefficients of drag for different shapes. So there you go. Get into that equation up there, drag force. All right, let's go back to V versus T. So this is velocity versus time for a falling object. Say it's falling off a cliff. But now let's consider air drag. What is that graph going to look like? Well, I bet during the first second or two of falling, when air drag is really little, it's going to be pretty close to like a vacuum. Right? You guys know what this graph would look like in a vacuum, right? It just increases at a constant rate. It's like a linear relationship. Right? But when air drag starts to build up, it's eventually going to reach terminal velocity. And suppose this thing does reach terminal velocity before it hits the ground. Now what's it going to look like? Bam! Probably something kind of like that. Right? It starts off kind of like it's in a vacuum, but then that changes. And terminal velocity, it's going to reach like a horizontal asymptote. Right? A plane at constant velocity. If it's constant velocity, that means it's in equilibrium. So all the forces better be balancing. I mean, it's got a huge weight. Better be some kind of lift force to balance that. I bet there's some air drag, so maybe there's a thrust to balance that out. Engines are blasted. Right? Are you guys thinking, bam, those four forces right there? Weight down, weight down, lift force up, thrust forward, bounces with the drag backward. Plane at constant velocity. Pulling a block at constant velocity. Well, I think this block has a weight down and a normal force up. There's an applied force from the spring scale and a friction force that's balancing out that applied force. Would that be true? Okay. And hey, this friction force and this normal force, they're related to each other. There's some material property called the coefficient of friction. You guys remember that coefficient of friction? Okay. Okay. Let's look at coefficients of friction for different materials. Right. So some of these are really well established, like steel and aluminum, or have this kinetic friction, the static friction. Right? These bottom three might be really useful if you're driving a car. Right. So if you have a dry road, that's really good. Right? You have a lot of control over the car. If you have an icy road, ooh, bad news. There's hardly any friction at all. Block in equilibrium on an incline. Could you guys draw the three forces acting on that block? Three forces on that block? You guys are able to do that? Three forces acting on that block? Right? There's a weight pulling it down. Right? There's a normal force. Oh, okay, whoops. Actually, I broke that weight into components, right? Which is going to help you figure out the next force. The normal force from the surface. You guys don't know normal means perpendicular, right? perpendicular to the surface, and that's equal to mg cosine theta. Right? And if it is in equilibrium, that means that, well, there must be a third force keeping this mg sine theta in check. Like, for example, a friction force, right? So you guys see 1, 2, 3 forces, right? And I broke the weight into components. So the net force is 0, right? So the block might be at rest or it might be sliding at constant velocity, one or the other. 3 elevators. The elevator on the left is accelerating downward. Oh, you guys see the weight is the same on all 3 elevators, right? But the one on the left, the tension is less than the weight. So there's a net force downward. The one in the middle, equilibrium, the tension up is equal to the weight down. Now, the elevator might be at rest or it might be moving at constant velocity. Maybe it's going up, maybe it's going down, maybe it's at rest. It's ambiguous. You wouldn't know from the free body diagram itself, right? But you would know accelerating upward. That's the one on the right. The tension force is more than the weight, which might be moving up, speeding up, or might be moving down, slowing to a stop. Either of those could be accelerating upward. Okay. Atwoods. So we got, we're doing time here. About till 3. Okay. Oh, really got a few minutes left. All right. See how far we get here. You guys were doing a classic double elevator Atwood. So all these statements are true. There's just Newton's second law of motion at the top. The second box is modified for this specific scenario, which was an answer to one of your labs. I had you guys derive this empirically. Okay? Those last 2 boxes are specific to each one of those masses. If you just hone in on one or the other mass, and you can use that to solve for tension. Let's do that. Here's a modified Atwood. And actually, the one we did in class as part of the lab was even simpler than this because I had you guys prop this M2 on a Hot Wheels car to get rid of that orange friction. Right. Again, right. Got Newton's second law of motion. Then the second box applies specifically to this setup. And those bottom 2 boxes are specific to each mass. You can hone in on each of those and solve for the internal tension that's holding those together. Okay. Car brakes to a stop. Could you guys draw a free body diagram like that? So the car is moving to the right and it has 3 forces on it. Its weight down, the normal force from the road supporting it, and a friction force, that's causing it to brake to a stop. You guys come up with that? Yeah, here's a little equation over here. The acceleration of the car is equal to coefficient of friction times the gravity field. Okay. Hey, maybe that's why if you're on an icy road with hardly any coefficient of friction, it's really hard to slow the car down. Ooh, right? It's one perspective anyway. Car turning on a flat track. Give you 2 perspectives, aerial view and a view from behind. So if the road is flat, then it can only turn because of friction. Right now, if the road is banked, it's a little bit easier. You might not even need friction to make a turn if it's banked. But this is the flat road, so there better be a friction force that allows it to turn. So from above, that's the only force you would see, and then the other forces are going like into and out of the page. Right. So from behind, it would look like this. Right. Weight down, normal force up, and friction force would be allowing it to turn. That would be forcing it that direction. Right. Vertical loop. Okay, well, I gotta stop somewhere. We got about 30 seconds till the bell. So yeah. Right. So next week, we might do more on this presentation. I also have to go over those 100 questions with you guys. You guys are gonna take that half page and hold on to that, right? Because we're gonna go over all those too. All right. So go and stop this here. Okay. And you guys have a great weekend, and I will see you guys on Monday.